Dear audience, we continue on the propagation models. I want to derive here a general propagation loss formula relating the propagation loss in dB with the electric field near the receiver in dB microvolt per meter. Note here that this equation is not a general equation. It is valid only for EIRP of 62.15 dBm only. If EIRP is not equal to this value, this equation is not valid. So I will derive an equation which should be valid for any EIRP. The received power is equal to the power density near the receiver, radiation power density, E squared over Z naught. E is the RMS value of the field near the receiving antenna, and Z naught is the intrinsic impedance of free space, which is 120 pi ohm or 377 ohm, or Z naught is the intrinsic impedance of the medium, whatever medium. And the power density times the effective area of the receiver should equal the received power. Effective area is lambda squared over 4 pi times GR. Lambda is the wavelength in meters, and GR is the gain of the receiving antenna. This is also the P received is also equal to P transmitted times G transmitted times G received over loss. This is general formula also. Now, combining these terms together here, to find an expression for E squared here is equal to 4 pi Z naught will be in the numerator here, 4 pi Z naught, and lambda squared will go to the denominator along with L, lambda squared times L, and PT GT will be in the numerator also. And GR will cancel with GR. Now, PT times GT is called EIRP, effective isotropically radiated power. E squared, this is squared here, squared is equal EIRP here, PTGT EIRP times 4 pi Z naught over L, and remember that lambda is equal C over F. So lambda squared is equal C squared over F squared. Here lambda squared, lambda is equal C over F. So this is equal to C over F squared. C squared will be here, and F squared will go to the numerator. Now we want to convert this into dB. 10 log this equal 10 log this. 10 log E squared is equal 10 log this expression here. 10 log E squared is equal 20 log E. 20 log E equal 10 log EIRP is EIRP in dB plus 10 log 4 pi Z naught over C squared. This is a constant for free space. C is of light, and Z naught is 377. Plus 20, 10 log f squared is 20 log f. Minus, because this is in the denominator, minus 10 log L, which is L in dB. Now, the 20 log E is E in dB, equal, this is in dB. If you put it in dBm, we subtract 30. So this is the same as this, equivalent, the same quantity. And if we substitute here, values for 4 pi, 4 times pi times 377 ohms divided by C, 3 times 10 to 8 meter per second squared, the result is this, and log times 10 equal, as you can see, minus 132.787. It is, we obtain the same value. So this is this. Now 20 log f, if we put f in megahertz, then we will add 120, because mega is 10 to 6. 10 to 6 times 20 is 120. So 20 log f is equal to 20 log f in megahertz plus 120. This is the also now. And finally minus LdB. Now if we put E in dB micro, we have to subtract 120. We have seen the equation, because E dB micro is equal 120 plus E dB. So E dB equal 100 E dB micro minus 120. So this is this here. EIRP minus 30 and minus 132.787 and plus 20 log f in megahertz and plus 120 minus LD in dB. If you combine these values, so L in dB here, if we take L to the other side here to obtain the loss of the electric field, we will obtain 120 will be positive here. We have EIRP in dBm, this quantity here, and we have also 20 log f in megahertz, this 20 f in megahertz, and we take EdB micro to this side, it will be here minus EdB micro, because we will take the other side, and the constant here will be equal to, let's calculate it here, will be 120 to the right hand side, will be 120 here, minus 30 minus 132.787 plus 120 is equal, as you can see, 77.213, exactly 77.213. So this is general equation. This is a general equation. So this is a general equation that can be used for any free space, any loss, for any medium, for any scenario, for any terrain, for any environment. So this equation is very general. It can be used for any situation. This is the loss in dB, and this equation does not exist in the book. This is in the textbook. So L in dB, the loss in dB is equal 77.213 plus the effective isotropically radiated power in dBm plus 20 log the frequency in megahertz minus the electric field in dB microvolt per meter. So this is the equation. We will use this equation. I have written this equation again here, the same equation. 77.13 plus EIRP in dBm plus 20 log F in megahertz minus L in dB. This is the path loss. This is E in terms of L, and here we have L in terms of E. Just we have interchanged the locations of L and E here. If you are given L, you can find E, and if you are given E, you can find L. Okay. This is a general equation for any propagation path, as we mentioned. Electric field at the observation point or near the receiver, and this is the frequency, and this is the path loss. A problem here: derive an equation for the field strength in dB microvolt per meter involving L and effective radiated power EIRP in dBm. E squared is given by this equation for pi mu naught. Mu naught is Z naught, the intrinsic impedance of the medium. Lambda is the wavelength, and L is the loss, and PT is the transmitter power. Eta naught, as we said, is 120 pi ohm or 377 ohm. Just we take the log of both sides, and we write E in dB microvolt per meter, and we will obtain this equation: 77.13 plus 20 log F mega plus LdB plus so L, we should always subtract L. If there is a minus sign here, we subtract the absolute value of L. If it is a positive sign, also we put the negative value of L. So always when we want to find the electric field, we subtract the absolute value of the loss. Now another question here: derive an expression for EdB microvolt per meter in terms of F in megahertz, EIRP in dBm for range d kilometer. This is derivation for the free space. Free space loss. As you can see, this is 32.44 minus 20 log D in kilometer minus 20 log Fm in megahertz. So we write here the electric field in terms of the distance and EIRP. We use the general formula because it applies to any medium. The general formula that we already derived a few minutes ago. We put here, instead we put here in place of the loss, we put the free space loss. This formula, this free space loss, we put this free space loss here, and we simplify, just very simple manipulations, we will obtain this equation. This equation gives the electric field near the receiver in terms of the distance and the gain and power power of the transmitter. And as we mentioned before, this is related to the universal equation, which gives the electric field, and it is frequency independent. Problem here: on a normal refraction day, which means standard atmospheric conditions, where the radius of the Earth or the equivalent radius of the Earth is 4/3 times the actual radius, which amounts to 6,378 times 4/3. The equivalent radius of the Earth, which is 8,497 kilometers. There is a dweller here on the building, and the building height is 16 meter, and he just sees the deck of a ship coming towards him. He is on the sea shore. We want to find the deck height here. From this distance is dt, which is equal square root of twice AEH1. We already derived this equation in the previous chapter. And this distance also dt2, dt1, dt2 is equal twice AEH2. Now the deck height, is given 9 meter, and the building height is 16 meter, and we want to find the total distance. So we find d1 and d2 and add them. To twice. AE is 8,497 kilometer, and the height of the building is 16 meter, and we convert it to kilometer because here kilometer and kilometer. Similarly here, this is AE, effective radius of the earth, and the height of the deck of the ship is 9 meter. We convert 9 meter into kilometers, dividing by 1000, and we get this value. Let's calculate it here. We have 2 times 8497 times 0.016 equal under square root, and you can see the value is here 16.49. here 16.49. The second value is 2 times 8497 times 0.009, 9 meters, equal under square root, and we obtain 12.37. as you can see, you add 16 plus 12 is 28, and 0.49 plus 0.37 is 0.86 kilometers. So the distance between the ship and the building is around 29 kilometers. Another model is Ibrahim and Parsons method. It is called the London model. They made a model following Okumura. It is more or less like Okumura model, but Okumura was in Japan, in Tokyo, and this is London model in London. It is similar to that, and we have a curve for a problem here. Question: find the exponent of power law with distance. Find the exponent of power law with distance for the Okumura measurements with the base station height of 200 meters at a frequency of 1 gigahertz, and the mobile height is 3 meters. We use figure 7.8. So we have the frequency of 1 gigahertz, and the mobile height is 3 meter, and the base station height is 200 meters, and we want to find the exponent of power law with distance. What's the meaning of exponent power law with distance? The loss is proportional 1 over d to the power n. L in the is the loss, and d is the distance between the transmitter and receiver. N is the exponent of power law. This is n. We want to find. So we go back to the curve 7.8 curve. Here 7.8 curve. The frequency is 1 gigahertz. 1 gigahertz here. It is 1000 megahertz. We make this. The frequency is 1 gigahertz. Here is 1 gigahertz. And this is the vertical axis is the loss, and the horizontal is the frequency, and here the distance between transmitter and receiver. The base station is 200, and the mobile height is 3 meters, and the frequency is, oh, let's write this here, 1000. We want to find along this line. Okay, this is the frequency, So we take different distances. Let's take 1 kilometer and 100 kilometers. The crosses are the Okumura. Let's consider Okumura. At 1 kilometer, the loss is 20 dB. At 1 kilometer, the loss is 20 dB. And at 100 kilometers, the loss here, this Okumura, crosses are Okumura, is, let's say, 61 or 62 dB, 61 dB. We know distance, we know loss, so we can find the power law. Yeah, we were here. Okay, so we said that at 1 kilometer the loss was 20 dB, and at 100 kilometers the loss is 61 dB. The power is proportional to 1 over d to the power n, or the loss also. The loss and the positive value, when it is positive, or the power, same, loss or power. The loss will decrease with the distance, sorry. So we should write here maybe, if L is a fraction less than 1, this means that the fraction, when you multiply, it will decrease with distance. If L is 1 over is greater than 1, you can use either system. If L is greater than 1, then L will be proportional to d to the power n. The power, of course, is always proportional to 1 over d to the power n. When you increase the distance, the power will decrease. The loss, it depends on whether you are using L less than 1 or L greater than 1. L less than 1, this means you are multiplying the power received by L. If L is greater than 1, this means that you are dividing the expression by L. Both are okay. Once, as far as you know what you are doing, then there is no problem. Now, 10 log the d2 over d1, is equal 61 minus 20. This means that, let me just explain this. P1 corresponds to 1 over P1 to the power n, and P2 proportional to 1 over d2 to the power n. Therefore, from this, P1 over P2 is equal, proportionality constant will cancel from here and here, equal d2 over d to the power n. Just direct division. Here P1 will be set constant divided by d1 to the power n, and P2 equal constant divided by d to the power n, and constant will cancel with the constant. And this is equal L2, the loss 2, if we consider the loss to be here the input of the power, over loss 1. Okay. If we take log 10 log for both sides of this equation, we will get 10 log d2 over d1 to the power n equal L2 minus L1. L2 is 61 and L1 is 20, so this is 41. And we d2 is equal 100 and d1 is equal to 1. So d2 over d1 is 100. This is 100. So all of this is equal to 100 is 10 squared. So this 10 to the power 2n. Which is equal times 10 20n. This means that 20n is equal to 41. Then n is equal 41 over 20, which is equal to 2.05. So n is equal around 2. This means that the power is proportional to 1 over d squared. If loss is greater than 1, then loss is proportional to d squared. If it is less than 1, it is proportional to 1 over d squared. Okay. Now let's use figure 7.9 here. And see the exponent of power law. Let's use 7.9. 7.9. That's 7.9. And let's consider this linear region. Now we said that the base station height was 200 meters, so we choose this curve here, 200 meters, and the mobile height is 3 meters here. Okay. And the frequency, there is no frequency here, so we use the we want to see the distance here, distance, the range, exponent power law. So we take 1 kilometer at 1 kilometer at 1 kilometer for this here, 20, 200, it is around 90, say 94 or 93 dB m electric field, dB micro volt per meter. For the same curve at 10 kilometers here, we have this here, it will be maybe also 63, 10 kilometer, around 63 dB microvolt per meter. Let's go back now and see our problem, our question. Here. As we mentioned, at 1 kilometer, the electric field, received electric field was 93 dB microvolt per meter, and at 10 kilometer the received field was 63 dB microvolt per meter. This is logical because when the distance is small, we receive higher electric field. When the distance is long, we receive lower electric field. Now, similar to the reasoning we have already used here, 10 log distance 10 over 1 to the power n equal 93 minus 63. Here we reverse the order because we are speaking about electric field, not okay. Okay, so this is 30, and in this case 10 over 1 is 10, log 10 to the power n is n, 10n is equal 30, so n is equal 30 over 10, n equal 3. This is the exponent of power law. it's a good idea to stop here. Thank you for listening.